Firstly, thank you ever so much for inviting me to take part in this conference. And when I was asked to talk about recent climate change, I realized that recent to me means something quite different to kind of the geological timescales that you presented at the beginning there. So I was asked to talk about recent climate change, but because the work that I do, so I head up the ice core group, that's the British Antarctic Survey, not BGS, sorry. And so much of the content of this talk is actually going to be focused around what ice cores can tell us, and going really from recent decades back to the past 800,000 years, which I do appreciate for this group is probably just a snapshot. Okay, so on a global scale, I mean, this is really telling us what we probably all know, but on a global scale, the 20th century, we've seen this as a period of quite rapid climate change. So these are the plots here from the recent IPCC reports showing this kind of warming from around 1900s. But really the important thing for, I guess, all of us is what we want to know is what's going to happen in the future. And that's really where much of our research is leading us. So these are some of the predictions we've got here from the 21st century. And the best guess that we have at the moment are from the climate models. But as you can see, there's quite a spread between the different models. And really what we need to do in the research community is provide our best understanding of how the climate has changed in the past to hopefully improve these climate predictions, because as we all know, it really does make a difference whether the climate is going to warm by 5 degrees as opposed to 2 degrees. So one of the best ways that we have to improve the climate models is looking in the past. And I believe one of the best archives of paleo change is the ice cores. And the reason for this is because in the polar regions, the snow never melts. So when it falls, it becomes trapped and forms these annual layers. So you can see this here in some of the images. So on the left, we've got an ice core looking down the barrel of the drill. And then what you can see is actually some of the layers within the ice and within a section of the ice core. And the water itself within an ice core can actually tell you something about past temperature, past surface temperature. And the thickness of the layers of this snow as it builds up can tell you something about past precipitation and past snowfall. The snow itself also brings with it a range of different impurities in the ice. So these can be natural things such as dust, can tell you about winds and circulation patterns, but also importantly can tell you things about pollutants in a more recent time. And these may have travelled from great distances as far as Australia and South America for the Antarctic ice cores. But the ice cores can help us to reconstruct the climate change over the recent period, over years to decades, but also back nearly 1 million years. And as such, this is what's really driven our understanding of the recent, I realize I'm using recent now in a geological time, the changes from these sort of large ice ages, glacial periods to the interglacials that we're in today. So I've put this up here because really what we're interested in, it's not so much the global warming as such, but the greatest impact that this is going to have to civilization is really how it changes sea levels. And so this is where we're going to see the greatest hardship and the greatest change. And I realized when I was putting this together very quickly this morning, much of my focus here is looking at how this is going to impact things. And, looking at the Thames Barrier is a very good example of how sea level is going to have a big impact on our country, but also looking to a more northern perspective. I looked at some of the structures that are classed as at risk of sea level rise in the next 50 years. And so there is areas in the north of England, so the Tyne Bridge and Holly Island, for example, which are listed as being at risk landmarks during the 21st century. I'm hoping this video is going to work. It's not showing up yet. Hopefully that's coming up on the screen now. So the inevitable thing really is that as the climate is warming, and we know this is happening, is that actually it's having a very big impact on our ice sheets. And so I'm focusing here on Antarctica, and this is a really important graph showing how Antarctica has been melting during just the last few decades, really, so from 2002. And in this period, this is from the satellite observations. I'll just see if I can replay that one again for you. We can see from the satellite observations that this is showing the increase in the mass loss, and this is having a very direct contribution to sea level rise. And particularly the areas that I want you to really focus on is, as you can start seeing this red area in the map, and this is West Antarctica, and this is a really important area for us because there's perhaps an opportunity or a potential that this area could have a very catastrophic collapse which would result in a contribution to sea level in the order of about 5 meters of sea level change. So the other interesting side of this story in looking at how Antarctica can really impact our sea levels is not just how much it melts, and we understand that as the climate warms, as the ocean warms, as we have changes in circulation, we're seeing an increase in the melt, but it's also how Antarctica can be helping us. It can also have a contribution to mitigate sea levels by taking up some of this water that would otherwise have ended up in the oceans. And so just through our basic physics, we know as the atmosphere gets warmer, we can uptake more moisture, we get more snowfall across Antarctica, and actually that becomes locked away. And so under a number of the future climate scenarios, we actually predict that the Antarctic ice sheet will act as a way of mitigating sea level. But as you can see, again, with any of the climate model data that we show, there's a huge spread in actually how much this is going to have an impact. And so this is where some of the ice cores have been really valuable in helping us to understand this. And so this is some work I've been doing in the last few years, where we've actually used all of the ice core records that we've got available from across Antarctica. And we've been able to show that actually the amount of snowfall during the 20th century has been increasing quite significantly. And in fact, the amount of snowfall during the first century of the first decade, sorry, of the 21st century was 272 billion tons more than at the beginning of the 19th century. And so that's the equivalent of twice the volume of the Dead Sea. So this actual increase in snowfall across Antarctica has mitigated the 20th century sea levels by 10 millimeters. So it was just really to sort of demonstrate that Antarctica is potentially a major threat, or as a contribution to global sea level, but it also has a role to play in mitigating sea level. But I guess really for the benefit of this conference, what we're really interested in is the greenhouse gases. So we are aware that a lot of these changes have been taking place during the satellite era, the melting, changing of the climate, as we've already kind of spoken about. And I think the finger is firmly pointing towards the greenhouse gas emissions. But we only have a very short observation period. And this again is where the ice cores become so important in extending our understanding. So what I'm showing here is the measurements of CO2 in the atmosphere, which first began in Hawaii about 50 years ago. So from the 1958 record here, and then the record in the darker red is showing the measurements at Halley Station in Antarctica, began in 1983. And so what these measurements show us is this kind of relentless increase in CO2 building up in our atmosphere from the end of the middle of the 19th century. But again, what we really want to know is, how significant is this increase? How does it fit within our longer term climate? And the best way of answering this again is looking at the ice cores, but more specifically, it's actually looking at the bubbles within the ice cores. So the picture you can see at the bottom here, this is a cross section from an ice core, and hopefully what you can see is the little bubbles within that. And what's brilliant in an in-person event is that you can actually show people the ice, you can handle it, you can see these bubbles for yourself. They are very easy to extract. It's not a proxy, we don't have to do a huge amount to it. It is literally as these bubbles are then broken open, the gases can be extracted. And this is what tells us about the past atmospheric composition. So now I'm extending the CO2 record here, going back further in time. And what we can clearly see is that the instrumental records shown in the red are lined up against what we see from the ice core to really put this recent increase in context. And so mentioning about when the Mining Institute began, it's about that time from sort of the 1800s onwards that we started to increase from the levels of pre-industrial conditions, where the concentration in the atmosphere is around 280 parts per billion, where we've gone all the way up to present. And at the moment, the concentrations in our atmosphere are 417 parts per million. But the ice cores can do much more, and they can take this back not just in the last few centuries, but actually take this back 850,000 years. And so this is the record now expanded all the way back. I'm actually only going back 650,000 years here, but what we can show is really just how much this recent rise stands out in the background. So what we can see here are these natural cycles as the climate's gone from the relatively warm periods that we're in today, the Holocene, and we've got previous interglacial periods, to these very cold glacial conditions. And the change in carbon dioxide is part of perfectly natural cycle to do with the size of the ice sheets during those changes. And so what we can see is that during the previous interglacials, these previous warm periods, the levels of carbon dioxide in the atmosphere stayed fairly consistently around 260, 280 parts per million during the warm conditions, and then reduced down to below 200 parts per million during the glacial conditions. Now, what's really useful and important is to actually show how this relationship with temperature has varied. And so I'm just overlaying on here, this is the stable water isotope from an ice core, and this is what we use as our proxy for past surface temperature. This is based on the isotopic composition and how they vary depending on temperature. But what's really important is just to show that this relationship is quite consistent. At temperatures, when they're warmer, we get more carbon dioxide. When they're colder, we have less carbon dioxide. But what we're really doing in the present is taking ourselves outside of this range of natural variability to a period where the amount of carbon dioxide in our atmosphere has increased at such a rapid rate, it's now sort of, we've separated away from this relationship with temperature. And really what we're trying to figure out in the scientific community is actually how is that going to pan out? What are the changes going to be in the next few decades, to certainly the next few hundred years? So I'm just going to finish up on that slide there. It's quite a powerful message of really what's going on. And so what I hope I've been able to show you is how ice cores are able to record carbon dioxide, not just in the recent period from the Industrial Revolution, but actually take this back and how carbon dioxide and temperature have co-varied over the last 800,000 years. So we know that the increases in CO2 in our atmosphere are a result of the warming air surface temperatures. This is one of the causes of it. And the biggest kind of threat to our community, to the planet really, is actually the changes it's going to have on our polar regions. And this is through the changes it's going to have with sea levels. We'll finish up there. Thank you.
Okay, thanks a lot, Liz. That was an incredible talk, and really highlighting our life in a 400 parts per million world now, and what we do about that.